Okay, so hi guys, in this lecture we'll be talking about the stereochemistry of Spiro compounds, and then we'll be looking at the stereochemistry of biphenyl. Okay, so for this first let us look at stereochemistry of Spiro compounds. Stereochemistry of Spiro compounds. So I hope you remember what are Spiro compounds. So compounds like this are Spiro compounds. Okay, so what we can notice is the two rings are actually not in the same ring, and they should not be, as they are sp3 hybridized bridgehead carbon. So it is something like going inside the plane and going towards your face, or outside the plane, coming up from the plane. And then we have the substituted atoms here at CS3 and HCS3 here. So in this case, okay, so first let me also write all the matrix points. So all the matrix point are obviously A is POS, B is COS, C is chiral compound, D is optically active. So if C is there, D would be always there. C, D, E. E is chiral center, and F is geometrical isomerism. Okay, so in the case of Spiro compounds, we would have something like this. So it does not have any POS or COS, but it's a chiral compound, because if we change H and CS3, we change the positions, we can actually get enantiomer. Okay, let us look at second example, wherein we have so second ring would be out of the plane for the first and third ring, hence first and third ring would be in the same plane, hence H and CS3 would both be in the plus Z and minus Z, these both. Okay, so it would be having a plane of symmetry. How? You can just pass on this as the plane which is parallel to these atoms CS3H and here CS3H. So it would have plane of symmetry. Would it have center of symmetry? Yes. These CS3 and these CS3 are diametrically opposite to each other. So next, okay, I think G point was also there. So G point would be, okay, so did I miss some points? C is chiral center, D is optically active, E is chiral center. Okay, F is C2. I can replace it with F to be C2. C2 and G would be GI, geometrical isomerism. Okay, so apart from A and B, can we have G and F as well? So yes, it can show geometrical isomerism, and it will show geometrical isomerism. Okay, so would F be there? Would it have axis of symmetry? So if we actually turn this into 180 degree about this axis, we actually flip it, then not exactly this axis, it would be something like this axis. So if we flip it across this axis 180 degrees, so it would have C2 axis of symmetry, hence F would also be there. Okay, so let us look at the second example, wherein we have this HCS3 and HCS3 here. So obviously this would be the same as the previous compound, means these two H and CS3 would be in the same plane, so it would have plane of symmetry. It would be obviously optically active, hence a chiral compound as well. It would have center of symmetry as well, yes or no? If you look at the center of symmetry, actually the previous case we missed on the center of symmetry. These two were diametrically opposite to each other, and similarly for H also. So C should be there, B should also be there here. No, we wrote the B point. Okay, B is already covered. Okay, so in this case, do we have center of symmetry? No. So what else we have? So F would be there. You can directly, the perpendicular plane to the compound, you can directly turn it 180 degree and it will result in the same compound. Okay, so would it show geometrical isomerism? Yes. Okay, so we have done examples on the stereochemistry of Spiro compounds. Next topic is stereochemistry of biphenyl. Stereochemistry of biphenyl. Okay, so suppose we have two benzene rings attached to each other with a bond, and we have four bulky groups attached on ortho positions of both the rings, where A and B can be anything from chloro, bromo, iodo, nitro, sulfo, or it can be carboxylic acid or simple alkane also. So A and B can take any atom from the box. So we would have something like this box, and so because of this steric hindrance, the we would have we'll talk about three things. That A is there is a steric crowding or steric hindrance in the compound, because of which the two phenyl rings will come in perpendicular to each other. So two phenyl rings are perpendicular to each other in this case, and C is it is a optically active compound. Okay, so let us look into some of the examples of it. We would have something like this. We have NO2 here, we have SO3H here, and same SO3H here also, and NO2 here. So this would be optically active. Why? Because the two phenyl rings are perpendicular to each other, so as to avoid the steric repulsion. We have another example like this, wherein we have Br I here, we have I and Br here as well. Okay, so in this case this is also optically active. Okay, let's look into more such examples. We would have Okay, we have Br and H here, and we have AsMe3 here. Because of its large size, still the compound is the two phenyl rings are perpendicular to each other, and because of that the compound is optically active. Okay, or we can also say this is a chiral compound. Okay, so just remember that achiral compounds are symmetric compounds and they have POS and COS. Okay, and the definition of chiral center is simply four different groups attached to an atom is a chiral center. So just repeating again, chiral center is nothing but four different groups attached to a atom is a chiral compound, chiral center. Okay, and what are achiral compounds? Achiral compounds. Achiral compounds are symmetric compounds having POS and COS. Okay, so this brings us to the end of this lecture. In the next lecture we will be talking about racemic mixture, and we'll talk about the summary of the chapter so far. Okay, so till then, good luck and goodbye.